This is section 5 from chapter 3 on continuous distributions, and this section is on the continuous uniform distribution. Now the name comes from the fact that the probability of x is uniform over an interval from A to B. In other words, the probability doesn't change regardless of the value of x. Now, since we know that probability is equal 1, which means that the area of this is equal to 1, if we want to find the height of this, we'll do 1 divided by the width. So it's like area divided by width equals height. And that will be a value of 1 over the area divided by the width, which is going to be b minus a. So the PDF for this, the probability density function, can be written like this. For values of x between a and b in this interval, the probability is 1 minus b over a, and it will be the same regardless of the value of x. And for anything else, so for anything else over here, the probability is 0. To find the mean, e of x, we do a plus b divided by 2, so we take these two endpoints, divide by 2. The variance of var x is b minus a, so this b minus a all squared divided by 12. And lastly, the cumulative distribution function, which we notate with capital F of x, is given here. Example 15. The continuous random variable x is uniformly distributed on the interval 3 to 5, and we need to find part A, the probability for x between 3.2 and 4.3. So the first thing I'm going to do is to draw a sketch of this distribution, and I can see that we're going between 3 and 5. It's uniformly distributed between 3 and 5, so we'll draw that in. And to calculate this probability, we're going to want to find the area between 3.2 and 4.3. So we'll just put some marks in for that. So let's say that this is 3.2 here, and 4.3, it doesn't need to be accurate, is here. So our job is to work out what this area is. So we've got the width of it. What we need is the height. Now, to find the height, we know that the area is 1 of the original distribution here between 3 and 5. So we're going to do 1 divided by, so we can say f of x is equal to 1 divided by the width, which is going to be 5 minus 3. So that's going to be 1 over 2, which is a half, or 0.5. So let's put that here. So the height of this is 0.5. So the area of that part that I've shaded purple is going to give me the answer to my question. So the probability that x is between 3.2 and 4.3 is going to be that area, which is its width, which is 4.3 minus 3.2, times by its height, which is 0.5. And that gives 11 over 20. Or we could give our answer as a decimal because it comes out as exactly 0.55. Okay, part B, we want to find k such that this inequality here becomes equal to 0.2. Right, so in answer to, or to enable us to answer this question, what we need to do first is to simplify that inequality. That's in the brackets here. Now we can start by adding x to both sides. So that will give us the probability of 3x is less than k is equal to 0.2. Then we divide both sides of that by 3 to give us x is less than a third, k is equal to 0.2. Now let's think about what this statement means here. That the area up to a third k equals 0.2. the area up to a third k equals 0.2. So if this value is a third k, here, this area that I've shaded in green, that area is equal to 0.2. That means that this width, the difference between a third k and 3, or a third k minus 3, times the height of 0.5 gives us an area of 0.2. So let's write this statement down. So basically what we're doing is the width, 1/3 k minus 3, times the height, which is 0.5, is equal to 0.2. And now we can solve this to work out what k is. So that will give us a third k minus 3, 3 times both sides by 2, equals 0.4. Then we add 3 to both sides. So a third k equals 0.4 plus 3, so 3.4. And then k will equal 3.4 times 3. And that will give us k equal to 10.2. 10.2. Now don't be alarmed, because that doesn't mean 10.2 here. That's the value of k, 10.2 minus x. So this is what satisfies the inequality. So don't think this is wrong because it's not 10.2 here. It satisfies the original question. And you can check it out if you want to. So for example, if we put k into this, we're saying that the area up to a third k, which is 3.4, is 0.2. So we're saying the area from 3 to 3.4 is 0.2. Now, if it's up to 3.4, then the width is 0.4 times by the height, 0.5, and we get an area of 0.2. So we can indeed check that the answer is correct by substituting this k into this statement here. Example 16. The continuous random variable x has PDF as shown in this diagram here. Part A, what we need to do is to find the value of k. So in any continuous rectangular or uniform distribution, that area is equal to 1. In fact, in any PDF for any function, the area under curves or lines, whatever, is going to equal 1, but it's just a rectangle. So we can use the formula. If you can't remember the formula, just think, well, area divided by width equals height. Yeah, 1 over b minus a equals f of x. So area divided by width, 4 minus k, is equal to 0.4. So this is just a matter of rearranging this to solve it. So we'll have 1 equals 0.4 times by 4 minus k. That will give us 1 equals 1.6 minus 0.4k. Take away 1.6 from both sides, so we've got negative 0.6 equals negative 0.4k, and then from there divide both sides by negative 0.4, and k is equal to 3 over 2, or 1.5. Right, now find the value of k. I'm going to put it onto the diagram here and put this end here as 1.5, because that now will help me with the rest of the question. So in part B, we want to find a probability that x is between 3 and 3.5. So that's going to be the width times the height. Now the width is the difference between 3.5 and 3, which is going to be 0.5, times that by the height, which is 0.4. So we've got 0.5 times 0.4. We'll get a value of 0.2. Moving on to part C, let's just highlight these answers here. Part C, we've got conditional probability here. The probability that x is greater than 3, given that x is greater than 2. Now it might be helpful to demonstrate how to work out this probability using a diagram. So let's draw our uniform or rectangular distribution here, okay, which is going between 1.5 and 4. And with conditional probabilities, it's the second part which is it's out of x is greater than 2, or you can think of that as being the denominator. That's going to be the denominator, right? So this is the denominator, it's out of x is greater than 2, right? So that's going to be the denominator there. And I want to work out how much of x is greater than 3 is in x is greater than 2. Now, where's x is greater than 3? Well, that's this. So how much of x is greater than 3 is in x greater than 2? Well, all of it is. So actually, we can go straight to working it out. Now, if we were to use the formula for conditional probability, which is this here, then the conditional probability formula will become this, just making this part A and this part B. But actually trying to use the formula like this, it may be difficult to work out what the top part is. But as we said, basically it's how much of x is greater than 3 is in x is greater than 2, and all of x is greater than 3 is in x is greater than 2. So the top part just becomes this. It's all of the probability that x is greater than 3. Now this is where a diagram like this can be helpful, because if you can visualize it, it becomes much easier to put those values in. So let's just put the height of this graph here, which is 0.4. Let's work out the probability that x is greater than 3. Well, it's going to be that width times the height. So the width is 4 minus 3, I know that's 1, but I'm just going to write it out fully, times by the height, divided by the probability that x is greater than 2. Okay, so it's going to be that width, I know it's 2, but I'll write it down, 4 minus 2, times by its height, which is also 0.4. So we get 1 times 0.4 at the top, which is just 0.4, divided by 2 times 0.4 at the bottom, which is 0.8, and then we'll just simplify that to a half. So the answer to this conditional probability problem here in part B, or part C, sorry, is a half. Use diagrams to help you work out what these types of things look like. Example 17. The continuous random variable x has probability density function given here. And in part A, what we need to do is to write down the name of this distribution. Well, we have a uniform probability over this width here, these values of x. So we call this a continuous uniform, or it could be rectangular distribution, or rectangular distribution. Part B, the continuous random variable y equals 12 minus 3x. Now, when you start seeing things like that, that type of coding, you want to think, right, okay, if I want to find the mean, and this is the same for discrete random variables as well, a times the mean plus b, and if we want to find the variance, so the variance of ax plus b, that's equal to a squared times by the variance of x, the original variance. Right, so that's probably going to be useful. Right, so E of y, well, y is equal to 12 minus 3x, so that's equal to the mean of 12 minus 3x. Just replace the y with 12 minus 3x, it's just a straight substitution. That's equal to negative 3 times by the mean of x, using what we've got up here. So negative 3 times by the mean of x, I don't really need the bracket there, let's just write negative 3 ex plus 12. That does mean we need to work out what e of x is. And what we said right at the start, that e of x is a plus b, 8 plus 3 divided by 2. So 8 plus 3 over 2, so that's going to be 11 over 2, or 5.5. Right, let's move on to part C then. And part C, it says the probability that y is greater than 0. Now there's a couple of ways we can do this, an algebraic way and a graphical way. Let me start by showing you the graphical way. So I'm actually going to draw the uniform distribution for y. Now to do that, I'm going to work out what the two ends are. So I just substitute 3 and then 8 into this. So 12, first of all, 12 minus 3 times 3 is 12 minus 9, which gives me 3. So one end of the distribution is 3. And then substitute 8 into this. 12 minus 3 times 8, 12 minus 24 gives me negative 12. So you can again have negative values. So you've got negative 12 over here. It's a rectangular distribution. So basically it's this. Now we know that area is 1. What we're interested in is the height of this. So this width here is 15. So the area 1 divided by 15, which is the width, 1 over 15 gives us the height of this, which is equal to 1 over 15. We want to find a probability that y is greater than 0. Now on this diagram, that's going to be this area here. That's the probability that y is greater than 0. So that's just going to be this width times by the height, and that will give us 3 times 1 over 15, not sure why I put a negative there, and that will give us, I think that is 1/5. So 3 times 1 over 15, 3 over 15, which is 1/5. So let's see if we get the same answer doing it algebraically. So if we're going to do it algebraically, we start by writing the question out, and then what we're going to do is replace y with 12 minus 3x. So this is equal to the probability that 12 minus 3x is greater than 0. And we're just going to rearrange that inequality. So we've got the probability that 12 is greater than 3x. Then we're going to divide both sides by 3. The probability that 4 is greater than 3x, oh sorry, not 3x, just x. And then we just flip it around, and we want to work out the probability that x is less than 4. So here's just a sketch of the probability distribution for x. And if I want to work out a probability that's less than 4, if we drew maybe a line here, and here's 4, and we want to work out this area here, then we've got a width of 1, in other words 4 minus 3, times by the height, which we're given, which is 1/5. So it's basically 1 times 1/5. I'll write it out in full. So this would be equal to 4 minus 3 gives us the width, 4 minus 3 times by its height, 1/5, and that gives us 1/5. So you'll see we get the same answer if we do this either the graphical way or we do it the algebraic way. So part C is 1/5. Okay. Part D, we have a probability which is conditional. So the probability that x is less than 7, given that x or y, sorry, is less than 0, y is less than 0. Now to do this question, these need to be written using the same letter, the same distribution. So we need to change that y to 12 minus x. So if we do that, we'll get the probability that x is less than 7, given that 12 minus 3x is less than 0. Now you may notice that here we've got 12 minus 3x is less than 0. Before we had 12 minus 3x is greater than 0. So we could go straight to this and just reverse the sign. But let's go through the working just to double check. So the next step would be the probability x less than 7, given that 12, add 3x to both sides, is less than 3x. then if we divide both sides by 3 and flip the sign, we do indeed end up with x is greater than 4. So this is what we're trying to work out. Probability that x is less than 7, given that x is greater than 4. So here we can use our sketch of the distribution of x to help us out. This is the denominator, the probability that x is greater than 4. So let's just mark that in. So we'll have a 4 here, and this area here represents the probability that x is greater than 4. So that will be my denominator. So it's out of that. So that is a width of 4, 8 minus 4 times by height of a fifth. And I want to work out how much of x is less than 7 is in here. So if I mark off 7, for example, so if I stick 7 here, how much of the x is less than 7 area is part of that shaded bit? So in other words, I need to work out what, let's get a nice color so we can see it, hopefully this one here. We need to work out that area. That doesn't quite work. Let's try a darker color. So yeah, we want to work out, that's the amount of x is less than 7 is in x is greater than 4. So that's going to be a width of 3, or 7 minus 4 times by a fifth. So that gives us 3 times a fifth divided by 4 times a fifth, and that gives us 3/4 for that conditional probability. Example 18. The continuous random variable x has this probability density function, this PDF, and in part A we need to start by finding the mean, and as I do with all of these questions is I draw the distribution out first. Right, so here's the drawing of my distribution. Now, one way I can work out the mean is you can look to see whether your distribution is symmetrical, and that's a valid way of finding E of x, the mean, without actually doing any calculations. And I can see by symmetry that my mean is going to be here. And to find that mean, it's going to be halfway between the numbers a and b. So to find it, I would do a plus b or b plus a and divide it by 2. So let's write a plus b over 2. So we can say that E of x, the mean, equals a plus b over 2, and we found that by symmetry. And that's a valid way of doing it if your distribution is symmetrical. So for example, the normal distribution is symmetrical and the mean is in the very center of that distribution. Part B, we need to find var x. Now this is an algebraic proof to find var x, so you might want to watch this through a couple of times, and you'll need to know this proof and be able to reproduce it in the exam, this proof from first principles. So we're going to start by using this definition of the variance, not the other one, which is x squared times by f of x minus the mean squared, because the algebra is a bit more straightforward in this proof here. And as we go through the proof, it's going to require us to know and use the reverse chain rule, and also this identity that is here. Right, so the next step now is just to substitute the mean, E of x, for a plus b over 2, which we've done here, and also f of x, the uniform probability here, 1 minus b over a, f of x here. Right, so the next step now is I can integrate this. Now, because this is linear, x minus something, it's not x squared or anything like that. This is linear. I can use the reverse chain rule to to integrate this. So I integrate the outside. So add 1 to the power, 3, divide by the new power, which is 3. Then multiply by the inside differentiated. Now the inside differentiated is going to be 1. So if I divide by 1, that's not going to change. And now I'm ready to substitute my limits. Also, at the same time, I'm going to take this 3 out and put it here with this other fraction I've already got. Right, so here's my substitution. that I've done. So replace x with b first of all, then replace x with a. And actually, if I were to write, for example, this b as 2b over 2 and this a as 2a over 2, it means I can simplify what's in this brackets. So I've got 2b minus b, which is this b, minus a. This bracket is going to become b minus a over 2. And in a similar way, this bracket here will become a minus b all over 2. So let's now simplify that. Okay, so that's done. Now the next step is actually now to use this identity here. You can see here we've got a minus b. We can change that so that we've got negative b minus a. Now at the same time I'm going to expand the bottom, so I'll get 2 cubed 8, and I'm going to take the 8 out as well. So now that's done, taking the 8 out here. Now because the identity says that a minus b cubed, or the negative of that, is equal to b minus a cubed, so we could take the negative over to this side. So actually the top of this becomes a negative. We've already got a negative here, so now it comes plus. So now in the brackets we've got 2 lots of b minus a cubed, and we're pretty much done now. So we've got 2, this denominator now will become 12, and also we can cancel out a b minus a from the cubed with the b minus a at the bottom, and then the whole thing then just becomes b minus a all squared over 12, which is what we'd expect it to be. This is what we know as the variance, but as I said, we need to know this proof from first principles. And lastly, part C, we want to find the cumulative density function here, the CDF, sorry, cumulative distribution function. So if we want to find the CDF, we find that by integrating the PDF with respect to x. Right, so let's put in the PDF, which is going to be integrating 1 over b minus a with respect to x. If we integrate that, we'll get x times by 1 over b minus a, or x over b minus a plus c. We want to find c. Now we know, for example, that the CDF is 0 when we put in a into it, so f of a equals 0, or we can use f of b equals 1. So let's use f of a. I'm just choosing that one. So we know that f of a equals 0. That basically means if I substitute a for x, that I can use that to work out what c is. So I will have a over b minus a plus c equals 0. So from that, I'll get c is equal to negative a over b minus a. So that means that the CDF f of x is going to equal this plus c. So in other words, this minus this. Since they're over the same denominator, I can write it as x minus a over b minus a. So x minus a over b minus a. Then the last step is just to write out the full distribution. So there's a cumulative probability of 0 when x is less than a, so over this side. Between a and b, the cumulative probability is given by this. That's what we've just worked out. And then the probability, or the cumulative probability, is 1 when x is greater than b. Now, this is given in the formula book, but it's useful to be able to prove it from first principles, but definitely for var x, that's something we definitely need to be able to prove from first principles. Example 19, the continuous random variable x is uniformly distributed over this interval, and we've got some things to find. What I'm going to do first is to draw what this distribution looks like. Okay, so here's my uniform distribution. It has a width of 3, an area of 1 divided by 3, which means that the height of this, the probability of it, is a third. And part A, I need to work out e of x. That's going to be pretty easy because we can just use the formula. which is a plus b over 2. So that will be 4 plus 7 over 2, 11 over 2, we can leave it like that, or 5.5. Part b var x, so the variance of x, again we can just use the formula, and that will be b minus a all squared over 12. I think in the formula book it says 1/12 at the front, it's the same thing. So that'd be 7 minus 4 squared over 12. 7 minus 4 is 3, so we've got 3 squared over 12, 9 over 12, which simplifies to 3/4, divide both by 3. And then part C, we need to find the cumulative distribution function of x for all x. So to find the CDF, you'll remember that we integrate the PDF. So let's work out what the PDF is for this. Well, basically that's going to look like this: f of x. Well, I'll write down all the bits, you don't need to do this. We'll have 0 for x is less than 4, and also 0 for when x is greater than 7. And then between the two, when x is between 4 and 7, we're going to get a probability of 1/3, which we worked out from our diagram here. That means if I integrate 1/3 with respect to x, that will give me my CDF. So let's do that. So that will be 1/3 x plus c. I need to work out the value of c, so I can either put x equals 0, I know the cumulative probability is 0, or x is 7, and I know that the cumulative probability is 1. So I'll put down here, I'm going to use the top one simply because the number is a little bit easier. So that will give me 1/3 times by 4 plus c equals 0. So 3/4 plus c equals 0, which will give, oh sorry, not 3/4, that will be 4/3 plus c, right? And that will mean c equals negative 4/3. So substituting that into here, that will give me 1/3 x minus 4/3, which we can write as x minus 4/3. We'll write the full PDF in a moment, but we can use the formula to do this. If you remember the formula to find f of x in this interval, the cumulative distribution function, it's not in the formula book, but it's worth remembering. That's going to be x minus a over b minus a. So that will be x minus 4 over 7 minus 4, which is 3. So we get the same result. So if you don't remember the formula, you can just integrate and then put one of the values in where you know the cumulative probability. We need to write the full CDF function. So f of x, like this. And we need to state the rule for all values of x. So we start with a cumulative probability of 0 when x is less than 4. And we're going to have a cumulative probability of 1 when x is greater than 7. Between 4 and 7, the way we're going to calculate the probability is x minus 4/3. Example 20, the continuous random variable y is uniformly distributed over the interval a to b. Given that e of y equals 1 and var y equals 16/3, find the value of a and the value of b. So this is using the formulas that we have for E and var. So E of y, well, the way that we find that is by doing a plus b over 2. So that's equal to 1. So we could say that a plus b equals 2. So there's one equation. We'll do the same for the variance, var y. The way that we find variance is that we do b minus a squared over 12. And that's going to equal 16 over 3. And if we times both sides by 12, we'll get b minus a squared is equal to 64. So here's our second equation here. So now it's just about solving these simultaneously. You've got different ways of doing it. I'm going to take this equation here and I'm going to make a the subject. So I have a equals 2 minus b. And then substitute that into the second equation. So replace any a's with 2 minus b. So I have b minus 2 minus b all squared equals 64. Then work out the bracket. So I have b minus 2 plus b all squared equals 64. From there, that will be 2b minus 2 all squared equals 64. Then expand the brackets and solve the quadratic. Now you could square root both sides at this point. As I said, there are various ways of solving this. So that will give us this. We'll take away 64 from both sides to give us a quadratic all on one side, so we get minus 60 here. Then we'll divide both sides by 4, so we'll get b squared minus 2b minus 15 equals 0. And we can factorise that to give us, let's see, minus 5 and plus 3 equals 0. So the two values of b we're going to get are b equals 5 or b equals negative 3. Right, so we've got two values of b at the moment. Let's see what values of a we get. So if b was equal to 5, then a would be equal to 2 minus 5. A would be 2 minus 5, which would be minus 3. But if b was equal to minus 3 here, then a would be equal to 2 minus negative 3. 2 minus 3, and that gives us 5. Now, on this interval, a must be smaller than b. A must be smaller than b. Here you would have 5 at this end and negative 3 at this end. That doesn't make sense. That's got to be lower. So since a has to be smaller than b, that means we take the top row here, and that will give us a equal to negative 3 and b equal to 5. So always check that your value of a is lower than the value of b. Example 21. The continuous variable x is uniformly distributed over the interval negative 3 to 5. Part A, want to write down the mean of this distribution. Right, so here's my sketch of it. I can use the formula to find the mean. So that's just a plus b over 2. So a is going to be negative 3 plus b, which is 5, over 2. That gives us a value of 1. Now you could also give the value of 1 by symmetry, because 1 is going to be dead center of this rectangular uniform distribution. And part B is asking us to use integration to find the variance of x. So we can't just put the values of a and b into the formula b minus a all squared over 12, although we could use that as a check to see if our answer is correct. So I'm going to be using this definition to find the variance. So I am going to need f of x. I have got the mean already. So let's work out what f of x is, the height of this distribution. So it's got a width of 8, an area of 1. So we know that that means that its height is going to be 1/8. So that's going to be f of x. So let's just substitute those in. So, and we'll put our limits in as well, which are going to be -3 and 5. So -3, 5, and it's going to be x squared times by f of x, which is 1/8. And then we need to subtract the mean squared. Now the mean is 1, so we're just subtracting 1 squared. Now when we integrate, what we're going to get is x cubed over 3, and we're doing 1/8 of that. So that's going to be x cubed over 24 between our limits -3 and 5. And we're going to subtract 1 from that. Let's carry on up here. And we can evaluate that now. So that's going to be 5 cubed over 24. So we're now just doing the substitution, minus -3 cubed over 24. And then from that we subtract the mean squared, which is just 1. That gives us 125 over 24. Minus, and it's going to be -27 over 24, and then subtract 1, and that leaves us with 16 over 3 for the variance of x. Now if we wanted to check that was correct, so this isn't the way that we'd do this question, but a check by using the formula, which is b minus a squared over 12, what we derived in a previous example. So that will be 5 minus -3 all squared over 12. So that's going to be 8 squared, 64 over 12. And if we divide top and bottom by 4, that indeed simplifies to 16 over 3. So there's a useful check there if you get time after completing a question like this. Okay, so here's a recap of this section. So you should now be able to do exercise 3E on pages 76 to 79 of the textbook.